we go. All right. So for today, starting out today on the administrative front. A week from today, we're going to have a quiz, and I'll give you the details of it on Tuesday. It's going to be in class, sit in every other seat. If you get time and a half or double time through ODS, just I'll let you know which preceptor is going to handle that. Just send an email. We'll reserve a room that's quiet where you'll be able to take the quiz as necessary. Reach out to us. We'll create a Google form. It'll be fine. The way quizzes work. I'm going to give you a paper. I'm going to post it later today. We know what paper it is, but we want to go through the supplemental materials and find a table or two that we can ask you about. It's actually, so the way the quizzes work, I'm going to give you this paper and you're expected to read it. You can print out the paper and you can write anything on the paper that you want. Literally whatever you want. Okay. You are not allowed to print out all the lecture slides from the last 5 weeks on the paper. Not that that gives you an advantage. It's just sort of tacky. Someone did that once. I'm like, just write down the equations. What's fair game on the quiz on the paper is anything I've taught you about, anything that I've taught you, anything that's come up in lecture, precept, or the handouts that's discussed in the quiz is fair game. You'll find in the quiz, I don't believe that there's regression mentioned in it, so I won't ask you about regression. We haven't discussed p-values yet, so I won't ask you about p-values. There's discussions of scope conditions and validity. I'll ask you about that. Does that make sense? Okay. The paper itself, I'll post on Campus Wire a little bit after class. It's actually really, really cool. There was in 2000, I think it was 2016 and 17, ISIS went through Iraq and a bunch of people fled because those were not good folks. And there were refugee camps in other parts of Iraq. And there was a woman who actually set up a soccer league, or I'm going to call it soccer because I'm American. There's a woman who set up a soccer league, and the soccer league was composed primarily of Christians who are a minority in Iraq, a persecuted minority. And then what she did was she populated half the teams with a few Muslim players. And then she measured with the teams afterwards, comparing the all Christian teams to the Christian teams with a few Muslims on it, feelings towards, racial feelings across these lines. And she wanted to measure the effect of playing in a soccer team on basically getting along with and thinking better of co-nationalists of a different religion. The takeaway of the paper, and you'll read it, is that this social science can actually be kind of cool, right? That's just kind of fun. That seems like a good thing to do. It doesn't all have to be uptight and staid. You can have a good time with it. And it was just a really fascinating design. I don't want to go too far into it because you're expected to read it. All right. Any questions on the administrative side of the quiz? We can revisit on Tuesday if need be. Okay. The old exam, I'll put it up on Campus Wire. We're going to stick closely to it. I believe it's 12 questions, and the way we work is we just start with last year's quiz, keep the questions we can, but adjust them as needed, and the questions that don't fit, we write new ones. So we'll be sticking really, really closely to the quiz, to last year's quiz. Okay. Any questions on that before we roll into material? Cool. So today we're going to talk a little bit, we're going to finish up a little bit with figures and talk about the logical fallacy. Then we're going to talk about lines as linear regressions and adding lines to figures as an analytic tool to help convey a point. Then we're going to talk about a linear regression model. All right, and those are the three things we're going to go through. So this came up in the problem set. This showed up at the end of one of the handouts. But one way we can conduct spurious inference, or which means arguing there's an effect when there's not, is through give me 1 second to re-find my words. I swear today. Okay. One common mistake that you can make in the social sciences is conducting ecological inference. And one of the problems with just mistaking ecological correlations or cross-group correlations with within-group correlations is it can lead to spurious effects, meaning uncovering effects that aren't actually there. The basic idea is that sometimes in data, and if you look at all the data, you'll see an effect. But if you break it down group by group, you'll find there is in fact no effect. What's happening is when you pool all the data, you're finding effects across groups, where in fact what we're interested in effects within groups. That sounds a little abstract, so we're going to make it concrete from this particular example. This comes from Healy and Malhotra, published in the American Political Science Review in 2009. And what the authors did, they looked across quadrennial US elections from 1988 to 2004, and they wanted to know the following. If an area gets more federal aid, more federal disaster relief aid, does that state reward the incumbent? Sorry, it's at the county level. Do they reward the incumbent? So let's talk through the mechanism for just a moment. It's simply that by dispersing relief aid to different jurisdictions across America, then the more relief aid you give, the more favorably people, respondents, and citizens will look at the incumbent's party. Do folks get the mechanism there? The more things you distribute, the more you're rewarded as a politician. Let's back that up, because we're going to look at disaster relief aid, or look at relief aid. Let's back that up for a second. What constitutes relief aid? By and large, if you read their paper, they're talking about money that goes to buying new fire trucks, new ambulances, and new materials for first responders. Does anyone in this room have any idea how much money is spent on first responders in their neighborhoods? No. Every year there's someone who is either or is related to a volunteer or firefighter. So, every once in a while there's someone. But by and large, one of the flaws with their proposed mechanism is that people are just unaware of this form of aid, right? In order to get credit for this sort of aid, you have to know that it happens. A second issue is the time horizon. One of my colleagues 25 years ago conducted a study in West Africa where he actually handed out money to people, right? He just randomized that politicians would literally give out money, and the effects dissipated after a few months. If you're following a little bit in politics today, there's the there's the Dependence Act, where everyone gets $300 per child. And that effect wears off very, very quickly. So the second thing pushing against this particular argument that they're making is that people don't keep track of money that they don't know how much money their local government gets. And then they don't keep track of things they get from the government for more than a few months. So that's what initially got me to start thinking about this data and about this data set in particular, and that I didn't buy the mechanism. I didn't think that people were going to keep a tally for 4 years of local spending on fire trucks in their area. Now, this turns out the problem is one of an ecological correlation. These are two overlaid density plots of the x-axis is change in the vote percentage for the incumbent's party. Okay. And the y-axis is density, but the two different densities that are there, the black line is the change in vote percentage for areas that get any relief aid. That's the black line. The red line is the density for areas that get $0 in relief. Okay, so this is just a summary figure conveying the basic point of the authors. They go through, they run regressions with different specifications, but this is their basic point, and this shows up in their final models that they select. Looking at this, does it look like counties that get more levels of get higher levels of relief reward the incumbent party more? It does. That black density plot is well to the right of the red one. Okay, that's a discernible difference. They're not laid on top of each other. Let's take this same data and break it down election by election. So in this case, the one with all of them is in the upper left-hand corner. Let me expand this out a little bit up on the screen for you. The pooled data, which means pooled means combined. The pooled data is up in the upper left-hand corner, and then it's broken down election by election from 1988 to 2004. Is there an effect in the pooled data? Yes. Is there an effect in any given year? No, right? And this is the puzzle of the ecological fallacy. If you pool all the data, you find an effect, but in any given year, there is no effect. So we're going to talk about what's happening and break that apart in just a moment. But which results, looking at this, which result do you believe? Which result is more persuasive analytically, the one that pools all the data or the 5 by year analyses? The by-election analyses, right? So why did the authors miss this? We'll talk about why it is mechanically, but the first point I want to make is that if you're making a causal claim of some sort, then it needs to hold within groups. When you pool data, it's this density plot up here is combining across election data with within election data. But our causal claims are about individuals at a given time, so it's always within election claims that we're making. Okay, so actually what's happening here mechanically, these are the number of counties. I'm sorry, these are US counties, then this is log disaster aid relief per capita. This is their major treatment variable. In most years, the median had 0 relief all the way up through 2000. Then in 2004, the median jumped from disaster relief per capita in each county, jumped from 0 up to 3.5 on a log scale. Okay. What happened between 2000 and 2004 that would prompt the US to spend massive amounts of disaster relief aid all over the country? 9/11, right? And here's the subtle part in this paper. Even back in 2000 and 2004, a majority of Americans voted for the Democrat, but a majority of counties support the Republican in our presidential races. That's just a stylized fact of all the elections we've had then and since, okay? The majority of citizens vote for the Democratic candidate largely because the Democrats tend to win densely populated areas. Just hop the Acela train and go up and down, and it's just all Democratic territory, right? But the Republican candidate gets a majority in more counties because they're less densely populated, but there's more of them. So the 2004 election was marked by 2 things. An increase in disaster relief aid broadly across counties because of 9/11, but also it was George W. Bush running against John Kerry, and he won a majority of counties because he was the Republican running. So the entire effect over this time period is driven by the fact that 9/11 happened and a Republican was running. And that's what actually drove their entire result. Okay. And we didn't find this, and in order to find this, we need to look at the data a little bit more closely year by year. Continuing along with scatter plots, just to talk about some scatter plots that can illuminate different trends. After 2016, this was the Trump-Clinton election, a fair number of political prognosticators, including both of the candidates, thought that that election was in the bag for Hillary Clinton. It turns out, if for those of who didn't notice, it wasn't. And then there was quite a bit of self-reflection in the political statistics community, wondering why did we get this so wrong, right? And here, one of the questions that was asked is, who swung the election for Trump, right? Like, where's the base of support? This figure along the x-axis has median household income, thousands of dollars on a log scale. And recall, when we talk about income, we always log things. So what you see here, on the y-axis is Trump vote share in 2016 minus Romney vote share in 2012. Our unit of analysis is the county. One thing to note in this figure, every dot is a county, but the area of the circle is proportional to the population of the county. For those whose 7th grade math brain is turned on, that means that the radius is proportional to the square root of the population, because pi r squared is the area. All right. So what you'll see is that for areas that have for counties that have a higher income, including the larger counties, these are the larger dots, Trump actually underperformed relative to Romney. Now, when you come over here, what you find is for smaller counties with lower average income, lower median income, Trump overperformed relative to Romney. And this figure is arguing that the swing in counties, at least the county level swing in the 2016 election relative to 2012, was driven by large counties shifting more towards Trump than they were towards Romney, and smaller counties shifting more towards, sorry, large counties shifting away from Trump relative to where they were with Romney, and smaller counties shifting more towards Trump relative to where they were for Romney. Okay, useful analysis. We can look at a similar figure looking at the effects of education. So this figure by county is the proportion of each county with a bachelor's degree or higher. This is along the x-axis. The y-axis is the same as in the last figure. And what you'll notice is that educated counties, large counties with a large proportion of their populace educated, the counties out here, ended up, Trump underperformed relative to Romney. So if there's a large proportion of your population with a bachelor's degree or higher, Trump did worse than Romney did. Trump 16 did worse than Romney 12. If you come over here, you see that counties where only 10 or 15%, so 1 in 6 people have a bachelor's degree, what you'll see here is that in these smaller counties, Trump overperformed relative to Romney. And the point of these two figures, I'm going to just back up and tell you what these are conveying. These figures are designed to convey a basic point, and I'm going to just tell you what that point is, but highlight some of the best practices that we see here. One is that the figure tells you several things. The dots, being proportional to the population, conveys more information than just a dot. So it's telling you what the large counties are doing and what the small counties are doing. The other nice thing about it is it's actually legible. It's a relatively simple plot designed to convey a point. The point being that there's a linear relationship between proportion of the county with bachelors of education and support for Trump versus Romney. Okay, so I'm just holding these up as particularly nice recent examples of figures that convey important points about the underlying data. When you construct figures on your own, they really do take a lot of thought. So please put time and care into them. Continuing along this vein, we're going to look at two figures using a line. Okay. So in this case, we're going to compare the Republican share of the two-party vote with Romney's 2012 share against Trump's 2016 share on the y-axis. And this is plotted against the line y equals x right here. States above the line are ones where Trump outperformed Romney, and states below the line are the ones where Romney outperformed Trump. Looking at this figure, two things come out. The first two things that at least jumped out at me. One is, do you notice how all of the states are roughly linear with y equals x? They're roughly correlated with the line y equals x. So, but the line shifts up. Do you see what I'm saying? If you were to fit a line of best fit to this data, it would be like the line y equals x here, but shifted up a little bit. What that's saying is that the distribution, the increase of Trump's support relative to Romney in 2016 was just on average a mean shift. Every state moved up a couple percentage. Every state moved up, eyeballing it about half a percentage point, about 1 or 2 percentage points. So the election in 2016, at the state level, was not driven by a few states going way up for Trump. It was driven actually by every state going up roughly the same amount of percentage point or 2 for Trump. And that's what comes out of this figure. This one is the one that gave people heartache, this figure. I was kind of sort of building up to this one. Because we wanted to know, most of the pollsters, we'll dig into this a little bit more carefully. Most of the pollsters predicted 2016 incorrectly. The only person who got it right was Nate Silver at 538 if you follow those things. So I really, really, really recommend looking at him. Okay? We'll talk about him a little bit too. So this is Trump's actual and forecasted vote share. To explain this figure, along the x-axis, it's the poll-based forecast of the Trump vote. So day of the election, what proportion did pollsters predict Trump getting? All right. In this election, it was the actual Trump vote. Oh, and by the way, this analysis hasn't quite, I haven't seen these analyses updated for the 2020 election, but I'll keep my eyes open for them. For the actual Trump vote, we see this here. So what this is saying is, if the pollsters exactly predicted the outcome, we'd expect the data to fall right along the line y equals x. If the data falls above the line y equals x, then Trump outperformed the polls, did better than the polls suggested. If it falls below the line y equals x, then Trump did worse than the polls predicted. And what you'll notice is the following. If we look down here in the blue states, which are states that Romney won and that Obama won in 2012, the states that were previously won by Democrats were mostly polled correctly. You see how this pretty tightly falls on the line y equals x here? Now, if you look up in this quadrant, what you'll notice is that the states that Romney won in 2016, sorry, the states that Romney won in 2012 are states where Trump outperformed the polls in 2016. So in this case, these states down here, these states over here, are above the line y equals x, which is telling us that the actual Trump vote was systematically higher than the poll-based forecast of the Trump vote. This means that when the pollsters got 2016 wrong, it wasn't a chance-based error. It actually looks more like they systematically underestimated Trump's support in a whole slew of red states. So the performance was right around here, but the actual outcome was, the predicted outcome was down here, but the actual performance was up there. So polls in 2016, polls actually missed. It wasn't a random chance miscalculation, they actually missed what was happening. And we'll discuss a few more times about some of the things that have been corrected since. And in 2020, a lot of these errors were fixed. All right. Okay. So we're finishing up on figures and plots and density plots and that sort of thing. And there have been a few times in this course where we've just put a line to data either manually or I've asked you to do it. Now we're going to start talking about the regression line, which is sometimes referred to as the line of least squares or the line of best fit. And we're going to talk a little bit about how they're constructed. You will be asked to run regressions, to put regression lines on figures and that sort of thing, and actually to report the coefficients. We're beginning that process in just a moment. To set expectations, I sort of treat calculating regression lines manually as like long division. I'm not going to ask you to do it manually only because you have a calculator, you have R in front of you. In my grad class, I actually asked people to do it by hand once, and it's just miserable. I have to be, for folks who've done, has anyone taken, I think it's 202, has anyone inverted a 3x3 or 4x4 matrix by hand? Okay, for those of you who haven't, does that sound at all appetizing? No, okay. So the trade-off is we're not going to do those sorts of things in here. In exchange for that, I want you to be, we're going to talk a little bit about the math a bit, and I'll explain what I expect you to know for quizzes and things down the line. But I also want to alert you to the mathematical machinery underlying this, so that when you finish this course and you start to hit a ceiling with your statistics and you want to learn more, you sort of know what avenues to pursue. All right? So here, we're going to talk about past versus future GDP growth rates. The data is from 2008 versus 2007. This is just going to be a toy data set where we're going to fit a regression. Okay? That is the point of this particular figure. Looking at it, in 2008 versus 2007, the relationship is positive. Right? There does seem to be eyeballing with some sort of linear relationship in the data. We talked briefly about Anscombe's quartet and nonlinearities and that sort of thing. This doesn't seem to have any pronounced sort of curvature or anything. It just looks like a linear relationship. So before you fit a line to things, I do encourage that you look at the data. All right. So in this case, countries that had a high growth rate in 2007 were likely to have a high growth rate in 2008, and vice versa. Those with a low growth rate in 2007 were likely to have a low growth rate in 2008. So that's what's coming out of this figure. So we're going to start thinking about regression lines. And there's a few different equivalent ways to state this. So we're going to run through them. One way to think about a regression line, we're going to need an outcome variable or a dependent variable, which we'll call yi, and an independent variable, which we'll call xi. So the question answered by the regression line is, given a value of xi, what line gives my best guess for yi? Okay, so if I give you xi, what's your best guess for what you think yi will be? That's one question that the regression line answers. Okay, it's possible to extend this to all sort of crazy machine learning type stuff, but we're just going to keep this to the regression line for now and realize that it's a best linear predictor. Okay. So yi is the outcome or dependent variable, xi is the independent variable, or if we're making any sort of causal claims, a treatment variable. Another way to think about it is, what is the marginal effect of xi on yi? That's what the regression slope is telling us. It's answering the following question. What is the effect of a 1 unit increase in xi on my predicted value of yi? Okay, so it's a slope. If I move xi up 1, what do I expect? What happens to my predicted value of y? All right. That's the question that's answered by the slope in a regression line. The reason this is useful is it allows us to relate an xi, or it allows us to relate some independent variable to some dependent variable by asking the following question. On average, if I were to move xi up 1 unit, what do I think would happen to yi? All right. There's 3 different phrases we'll use for it. Sometimes you'll see it referred to as the regression line, sometimes as the line of best fit, sometimes as the line of least squares. All 3 of them are just equivalent. They're the exact same thing, just the language, it can be referred to in multiple ways. So what we're going to do is determine the line of best fit or the line of least squares. All right. Continuing the example from earlier, yi is going to be the GDP growth rate for country I in 2008. That's how we've measured yi. Xi is going to be the 2007 GDP growth rate for country I. That's just what xi is. This is all data that's available. So we want the line alpha plus xi beta, where alpha is going to be the intercept and beta is going to be the slope. Okay. And we'll go into this terminology, but alpha in this language is the intercept, beta is the slope. Can we say that y equals alpha plus xi beta? Let's take a look. Can we say that y is alpha plus xi beta? Does the line fall on a perfect, does all the data fall on a perfect line? No, right? So it's simply not true that we can assume this as a model. Y is alpha plus xi beta is just simply not true because the data don't fall on the line. So what we're going to do is establish an equality between the observed value and the expected value by adding on something called chance error. Sometimes it's called, some authors call it chance error, sometimes it's called the residual, sometimes residue, sometimes the error term. There's a number of different words for it, but what it's doing analytically is it's connecting the line of best, it's connecting the line to the outcome. Okay, so we'll get into this geometrically in just a moment. But the first distinction we need to make is between our assumed model and our fitted model. This is going to be our assumed model. We are going to assume that our outcome, 2008 GDP growth, is equal to alpha, some constant, plus a scalar times xi, plus an error term. This is a model we make by assumption. We will make various assumptions along these lines throughout the semester, but this is an assumption. Okay, we don't claim it's true, it's just a form we assume so that we can proceed with our analysis. Now, after we see our data, we're going to estimate a model. And we're going to estimate alpha hat, we're going to estimate alpha and beta with alpha hat and beta hat. This requires just a little bit of notation. If you see a hat over something, that means it's an estimate. All right. So we assume this model, then we see our data, and we say, R, what is the intercept and slope? And R is going to return two numbers, alpha hat and beta hat. That's going to be the intercept and the slope. The important distinction is that the assumed model, we assume it's the truth so that we can proceed with our model. The estimated model is a function of the data. So if we were to get one data set, we'd get an alpha hat and a beta hat. If we were to get another data set, we might get a different alpha hat and beta hat. All of those are estimates, so we want them to be close to the true alpha and beta, but none of them are the true alpha and beta. In some sense, we want to know what this alpha is and what this beta is because it's the true linear relationship. We don't know the true linear relationship, so instead, we have to estimate it using alpha hat and beta hat, which are functions of the data. Another way to think of this is if we think we run a survey and we test some outcome and we model it this way. If we sample one group of people, we're going to get a good estimate of alpha hat and beta hat. If we sample another group of people, we're going to get a different estimate of alpha hat and beta hat. Both are going to be perfectly fine estimates, but they're not going to be the exact same number, and neither one of them is going to be the truth. The goal of inference, which we'll return to after we understand the regression a little better, is asking ourselves, how close do we think alpha hat is to alpha? How good of an estimate is alpha hat? And how close do we think beta hat is to beta? And that's the question we'll get to in a little bit. But first, let's just talk about the mechanics of constructing this sort of line. So we need to think geometrically for just a moment and ask how far is a point from the line? All right. So the distance from one point to the line is called the residual. So if I want to know how far this point is to the line, that's how far it is. It's a good distance to the line, but this is an actual number, right? It's 10 to about 22 or 23. So this distance is about 13. So this point is about 13 units, 13 percentage points below the line. That's how far away that point is from that line. What we're going to do is for a given line, we can measure not just how far away one point is, but we can measure how far away all of the points are. Okay. Now, what this is doing is giving us a measure that depends on our observed sample, but it's giving us a way of thinking, here's a line, how far away is it? Here's another line, how far away is it? And if you were to draw any line, you could actually construct the residuals and figure out how far away the data is from that line. And that's what we're going to proceed to do with the method of least squares. So we're going to refer to it as a line of best fit. So let's look at this for a second. Best implies we should be minimizing something. So how far is this point from this line? And the answer is y minus alpha minus xi beta squared. Right? Remember, we need to square things to make them positive to be a distance. So how far, if you give me an alpha and beta, how far is the data from that line? And the answer is we're going to take these squared residuals here and just add them up. And that's called the residual sum of squares. It's a measure. If you give me alpha and beta, I can return a number to you that tells you how far away the line alpha plus beta x is from the data. Okay. So those of you wondering may go, well, can't we actually find the minimizer alpha? Can't we find the alpha and beta that minimizes the residual sum of squares? Or to put it differently, can't we find the estimated alpha and beta that gives us the line that's as close to the data as possible? And that's what we're about to do. A minor sidebar in that we're about to skip over 2 slides that I had presented one year. It turns out that you don't need calculus to solve this problem. This is actually a quadratic in beta and alpha. And then if you recall for the parabola ax squared plus bx plus c, the minimum is negative b over 2a and 4ac minus b squared over 2a. And for those of you who don't quite remember all of that, there's a 7th or 11th grade teacher somewhere that's choking up a little bit. But one year I worked through all the hairy algebra for 20 minutes in front of everybody. And everyone was like, oh my God, by the end. So what we're about to do is just present the results and we'll talk through them a little bit so you can see what the calculations look like and what the answer looks like. If you're interested in these calculations, talk to me afterwards. I also want to highlight that if you continue through the SML certificate, at some point you're going to do these sorts of calculations so that you can see what's making these models work. All right. So the correlation coefficient, if you'll recall, I just reproduced it here, is the covariance over the standard deviation of x times the standard deviation of y. Recall it's designed to run between plus or minus 1. The least squares coefficient is beta hat, is going to be the covariance over the variance in x. And you can go through and derive this if you want. I'd be glad to show you. What this is telling us, though, is that the regression coefficient is actually closely related to the correlation. Rearranging terms, the regression coefficient is the correlation times sy over sx. So what's the takeaway from this? The takeaway is that the regression coefficient and the correlation statistic share the same sign. If two variables are positively correlated, then regressing one on the other will give you a positive slope. Okay? And all of these are closely related concepts. What we're going to do for the last few minutes in here, we'll circle back to those slides, but I want to talk about these few slides for just a moment to illustrate where we use regression lines, in part because it comes out of the question that I asked you today. Todorov et al., I think it was around 2010, had a science paper. The link should be accurate, should be active. And they had a paper called Looks in Politics. For those of you in the politics department or taking courses in the politics department in American politics or American comparative in particular, there was a stage in the study of politics where people were like, oh, people look at candidates and assess the policies they expect them to deliver. And that's how they go ahead and choose their candidate. They might look retrospectively and say, how well did these parties or people do for me in the past? They might be prospective voters. How do I expect them to go in the future? You know, there's a variety of theories floating around. But at the heart of every one of these theories, for quite a while, was this idea that politicians, if elected, promise policies. And then voters either reward or punish these politicians based off how the return policies match up to their preferences. Okay? There's a number of different ways to state that, but you know, if you want policies that look like this, you vote for that candidate who's closer to you. Does everyone sort of understand that sort of model of vote choice? It's it's endemic to my field. It's not even necessarily wrong, but it's definitely one of the central models for how voters make choices. And it's not ludicrous either. This paper was a little bit jarring at the time because it said there's other things in play that are substantively important. Okay? So let me ask you this: look at these two candidates on the left and the right. Can I just get a show of hands? Look at them for just a moment. Who thinks the candidate on the left looks more competent? Who thinks the candidate on the right looks more competent? Okay. Guess which candidate won this race? Does anyone recognize the candidate? No, Russ Feingold, senator from Wisconsin. Okay. So the person on the left was Russ Feingold from Wisconsin. The person on the right is whoever Russ Feingold beat that year. Forgot his name. But hands went up that Russ Feingold just looks more competent, right? And we can't even attribute this to race or gender because these are two white guys, right? So what is it? Can you put your finger on it? What makes the picture on the left look more competent? Give me. Can I just get? I hear a bunch. Can I just get hands real quick? Yeah, just go ahead. Just shout it out. Smile. They're both smiling though. Okay, the one on the right looks like a creeper. Okay. What, I mean, I want to get at this because a large part of social science is trying to peg down these ineffable qualities like competence. Yeah. Really? Okay. Any other thoughts? Yeah. Okay. What I want you to do after the last couple conversations, looking straight a little bit, not looking like a creeper, the lighting, looking straight in the eyes, the particular pose. Go back to the answers that came up earlier at the beginning of the class of what politicians you find attractive and competent. That was a reference to what was coming now. And explain to me why Bernie Sanders looks competent. Like the man's hair is worse than mine. And I just can't, I don't know. Maybe I need mittens. But the disturbing part of this study, we'll get to the results in just a moment. The disturbing part of this study is the fact that they found evidence that voters reward candidates that look competent. What does looking competent mean? Well, let's see how they did it. In this study, what they did was they showed people pairwise pictures and asked them to rank both candidates on a scale of, I just want to make sure I get the scale right. Oh, they'd show them pairwise and then just ask people who looks more competent, left or right, left or right, left or right. They did all these pairwise comparisons and recorded the proportion of the participants that thought that one candidate looked more competent than the other. So like we just did this with this pair up here, and it was about a 90-10 split in here. 90% of the people thought that Russ Feingold on the left was more competent looking than the person on the right. All right. So that was the treatment variable, how competent they looked. It was 90%. Then what they did was they matched that number up against the actual vote returns. Does that make sense for folks? Okay. We might have to dissect the regression line in just a little bit. We might have to save that for the next lecture, but here are the results. And what you'll notice is here this 0 dash is the margin of victory. So these are observations for, right here it's a tie. These are races where one person won by a lot and one person lost by a lot. And here is, along this axis, is the proportion of participants that found that person more competent, looking more competent. And what you'll see is that there's a pronounced linear trend. Even absent the line of best fit, you sort of see that upwards trend in there in the data. It's not wildly pronounced because we don't expect that decisions for who should be elected to the Senate are driven entirely by looks. But judging by John Ossoff's fan base in this class, there might be something to that. So we find a pronounced effect. It doesn't override party necessarily, it doesn't override ideology necessarily, but it's measurable and it's substantively significant. To give you an idea, if someone were to go from 0% to 100% on competence. So can someone give me a politician who looks 0% competent?
Boris Johnson.
Who?
Boris Johnson.
Boris Johnson. See now, are there people who find him looking competent because he's too busy like thinking or something to dress well? Okay, we'll go with Boris Johnson. I don't want to start an international incident, but I will run with Boris Johnson. Largely, and I'm going to take that largely because I say soccer instead of football, so I need to like give something back. Which candidate looks competent, 100% competent? Ronald Reagan, right? The dude was born on a movie poster. So in that case, this figure is telling us that if someone's assessment goes from Boris Johnson to Ronald Reagan, we'd expect their vote return to go from losing by 40 points to winning by 40 points. And that's the estimate. And that's kind of a jarring amount, right? One takeaway from this, and I just want to finish up with this particular point. We don't want to do those sorts of hypotheticals of someone moving from 0 to 1. Every year, someone also mentions, I think D's Nuts is a presidential candidate every cycle who ranks as a 0 in competence. So in that case, you don't want to go from 0 to 1. You want to do something more reasonable. Like if I'm just going to take Boris Johnson, if you were to sit down with a tailor and a hairdresser, you could go from 0 to 5%. Right. So the better measure here isn't if you go from 0 to 100. It's if you can go if a 1 percentage point increase in assessed competence leads to a 0.7 percentage point increase in expected vote share. And if you look at the close elections we've been having in this country, 0.7 percentage points is enough to swing entire races, large numbers of them. We'll start off with this figure next time.